which is neural networks. Okay, so neural network is a very popular method because the performance is really very good, and it is very flexible in terms of the models that you can fit. It allows for many different ways in which you can train data. Okay. But the downside is that what's actually happening inside the black box is very hard to tell. We know what the general procedure is. Lots of things go on inside the box, and the parameters you can't really interpret. Like if you have slope coefficients in regression, you can do some interpretation with it, right? You can't do any of that in neural networks. And the danger is, of course, like in decision trees, you can overfit. Okay, you need to watch out for that. You don't want to overfit the data. Okay, so the general idea is this. This is the reason why it's called neural network. So this is how the brain cells work. That's the metaphor that's used in this modeling. So we have like our our what do you call these eyes and ears and so on. So they receive our body parts receive inputs from the external world. Okay, so we have inputs coming in. Okay, and they are transmitted into our brains. Okay, and then the brains interact, then they make sense of the world, right? So our brain has a number of neurons, and connections are made, and on and on and on. Synaptic connections. Okay, so you know more than how the brain works than I do, I bet. But this is the general idea about neural network. So you have inputs coming in. Okay, of course, in a human sense, we receive uncountable number of inputs, various inputs, sight, sound, and smell, and all that kind of stuff. And similarly, we have inputs coming in to the system. Okay, so combine input data in a complex and flexible neural network model. So this is how it works. So you have what is called an input layer. So input layer is where you have inputs coming in, and we have one node for each input. Okay, so in our data modeling context, this will be like predictors. Each predictor is an input. Okay, so you have 15 predictors, you have 15 nodes in the input layer. Okay. So if you have in the case of in the example that we're going to see, there are only 2 input, so we'll have only 2 nodes in the input layer. Okay, so there is input layer, and then at the other end we have the output layer. Output layer is the target. Okay, so if the target has 2 possible values, you will have 2 nodes. Okay, well, sometimes you can just simply represent one node because the other node is the opposite of the positive case. So you may want to just simply have the positive case as a single node, but we will use 2 nodes, positive case and the negative case. So 2 nodes in the output layer. Now if you have non-binary target, suppose if the target has, like the example that we just saw, 3 possible values for the target, then the output layer will have 3 nodes. Okay, so in the output layer we'll have 1 node for each possible value of the target. Okay, and then in between you have the hidden layers. So this is where the brain works. This is the brain metaphor. This is our synapses here. Okay, these are neurons, and these connections are made in synapses, and then you process the input, and then give the output. Okay, say, okay, this is my prediction. This is what this is. Okay. Now, how many hidden layers should you have? So in this diagram, we have 2 hidden layers. Okay. So we can have 3 hidden layers. We can have 4 hidden layers. Okay. Of course, the more hidden layers you have, the more complex the problem gets. Okay. That's one parameter that we need to think about, how many hidden layers to have. And then within a given hidden layer, how many neurons should you have? How many nodes should you have? Okay. Now, the input layer and the output layer, we know exactly how many nodes there has to be. In the input layer, the number of nodes is exactly equal to the number of predictors we have. The output layer, the number of nodes is exactly equal to the number of categories for the target. Okay. Now, in between, okay, you have to just trial and error. Okay. By trial and error, you figure out how many hidden layers to have and how many neurons you should have for each hidden layer. Okay. So this is the general architecture of a neural network. Okay. So multiple layers, you have input layer, you have output layer, and then you have hidden layers. And then we have nodes, and the nodes we have regression model like, okay, it looks like a regression model functions. Okay. So you have weights, and we use these weights with the values of the observations to find scores. Okay. So let's say, so here is an example, and this example has only 6 observations. Okay. So we have some kind of snack, and it has a fat score and a salt score, and then whether that snack, okay, whether the consumers accept or grade it as good or bad. Okay. They like the snack or they don't like the snack. So that's your target. Okay. So here is one way of designing this neural network. Okay. Here we have 2 predictors, salt score and fat score. So that's your input layer. Okay. Fat and salt, right? And then output layer, I don't like it, I like it. So 2 nodes. So in between, okay, for our example, for this example, let's assume there is only 1 hidden layer and there are 3 nodes in the hidden layer. Okay. And we will go through the computations, how it is done. Okay. So what will happen in actually when you train the data, the first observation, right? So you will start the process by assigning all of these weights, the initial weights. So you'll have W13, W14, W15, and 2, 3, 2, 4, 2, 5 going into these 3 nodes, and then there is what is called bias. So you have a bias for this node, bias for this node, bias for this node. So what you would do is you would go to this node, and these are the 2 inputs coming in. Okay? And then you have the bias. So you take these 3 values, okay, and combine them in some way. Okay? And then with that, you produce an output value. Do the same here. You take these 2 input values and the bias and combine them in some way, okay, and then produce an output value. Do the same here. Okay. So this is for the first observation. First observation is 0.2 and 0.9. So 0.2 and 0.9 goes here. So 0.2 and 0.9 goes here. 0.2 and 0.9 goes here. Then you do the computation. Out comes values from these 3. So for 6 and 7, now you're going to get 3 inputs. Okay. So each output from a hidden layer now is the input for the next layer. So you get 3 inputs into 6, you combine them with its bias, and then you make an output. Okay. you do the same thing here. And then compare that output with the actual value. The actual value for the first observation is 1. So that's this. So what is the predicted value? Subtract the actual value, subtract the predicted value. So you get an error. And you 0 for this like minus the predicted value, you get an error there. So you have 2 errors. Now you combine the 2 errors and take those errors to adjust these weights. So you do a backward pass. Okay? So if the error is big, you will make large corrections to all of these weights. If the error is small, you will make small corrections. Okay, so you go back this way. All right. So that's your first observation. Then you go to the next observation, you repeat that. Repeat this process of forward pass and backward propagation. Okay? So, and then you do the third observation, and then the fourth observation, fifth observation. So once you complete all the observations, so that is called one epoch. You have gone through one iteration, and in one iteration you process one row at a time, go forward, compute error, come backwards, adjust your weights. Second observation, repeat. Third observation, repeat. So you go through suppose you have 10 million observations, you'll do this 10 million times. So that will be one iteration. And then go through a second iteration, a third iteration, and so on. And you keep repeating this until you get to a point where the adjustments that you make to the weights is very small. So that is called converging. Okay? So when the model converges, then more iterations is not improving the weights anymore. So that is called convergence. So then you stop. Okay? And the initial weights, okay, the bias called theta, and the weights are typically somewhere between minus 0.05 and plus 0.05. And you don't have to specify this. The methodology will automatically assign random weights as initial weights. But if you do want to experiment with weights of your own, you can specify them. Okay? And again, these are arbitrary weights. There is no rule or anything like that. Okay? And then you go through the computation.